This is lesson 48, BHDL example 29. In the last example, you remember we used the plus sign to make a 4-bit adder. It'd be nice to be able to make an n-bit adder using a plus sign. And in fact, that's easy to do, as we'll see in this lesson. Here's a VHDL program. We'll call it adder VHD. This is one that you might want to use. We'll just make it an n-bit one by using our generic statement we've seen before. So in the entity we put generic n integer, colon 8. Now A is an input n minus 1 down to 0, B is an input n minus 1 down to 0, and Y is an output n minus 1 down to 0. B8 was just default. We've seen in the past how you can set it to whatever value you want. When you do a port map statement, you'll get a generic map statement there. So in the architecture, all you say is Y is just A plus B. It's that easy. Now, in this case, of course, we don't bring out the carry flag and overflow flag. We saw in the last lesson how you could do that if you wanted by just making the size of A and B 1 bit bigger than you need. Well, let's do a simulation to see if this works. Here's the 8-bit one. So A is 8 bits. These are hex values. And we're adding it to hex 33. And Y is 11 plus 33 is 44. 33 plus 33 is 66. And so forth. 7 plus 33 is AA. So that's the easy way to make an adder. Now, what's really going on here? Well, I told you needed that unsigned VHD program from the IEEE library, so you need to have this statement at the beginning of your program. And this unsigned is a VHD program which calls an arith VHD program. And in that arith, it shows you what happens when you make a plus sign. It turns out a plus sign calls this function plus, where the parameters are a, b. They're shown signed here. It turns out that in the original VHDL, you could only add signed or unsigned numbers, and they were defined in this arith VHD program. But everybody used standard logic as the type for their signals. So eventually they developed this unsigned VHD program, which basically overloaded the plus sign so that when you use standard logic types, it would behave like an unsigned, or signed in this case. As we've seen, there's no difference in the addition between unsigned and signed. You get the same answer. It's only whether the overflow flag will tell you whether the answers are correct or not. But look how they actually implement it. This plus function, they make a variable bv, that's which they're going to set to b down here, and sum, and they're signed a tick left down to 0. So a tick left means the most significant bit. And then they just have a for loop. For I in 0 to a tick left, that's however many bits you have, sum sub I is AI exclusive ORed with B variable I exclusive ORed with the carry. Well, that's just our logic equation that we derived for the sum. And the carry, if you remember when we did the Carnot map for the carry, we actually derived this equation before we changed it into the exclusive OR. It was AI ANDed with BI, or AI ANDed with the carry, or carry ANDed with the BI. That was carry I, which gets set to 0 to begin with, and every time through the loop it's the new carry which goes into here to produce the sum. So every time through the loop you're creating a full adder, exactly the same full adder we derived in previous lessons. And so you can make an n-bit one by just making n copies of it. So every time you use the plus sign, say in this program here, it actually implements, because you've called use IEEE sign, it actually implements in hardware a full adder of the same type that we've designed previously.